Hi, welcome back. Sorry, I didn't realize I ran out of time in that other video, so let's go back to myself over. Let's go back here. Oops. Okay. So what I was doing previously was actually solving this, including the weight of this. So let's finish this up. So I was analyzing the torques on our system, our clockwise versus our counterclockwise. So this one is going to go clockwise. There we go. So it's clockwise. This one's also clockwise. Oops. And this one's going to be our counterclockwise because it's going opposite like that. So with that said, we can now write our expression. Let's move this down a little bit for our torques. So our torque counterclockwise will be FB times its radius from the pivot, so it's 1 meter. Now notice that this is at a right angle, so we don't need signs. So now I'm going to subtract my counter. So assuming this board is uniformly, massed, the center of the mass will happen at the center of the board, which is officially, if this is 1, this is 3 at 2 centimeters. So, 2 meters. So I call this FG1 times its radius, 2 meters, minus FG2 and its radius. We're going to set this equal to, of course, 0. And just to expedite things, this is nicely 1, and all these can move over, so FB is going to be M of the board, G times 2. Now this is added over, and this is also added over, so MG2 times 4 meters like that. This is the person. So the board is 35 kilograms. Let me just double check. Yes, it is. Times 9.81 times 2 plus this one is 58. 9.81 times 4, and then when I calculate that out, I get 2962.62 newtons for my FB. So we're closer to 3 here, so as you might imagine, since there's an extra weight on this, the board will push up with more force. That makes sense. And then this was part 1. So part 2, now I'm going to use that number for here, 2962.62 minus FA minus M, which I called this one, 9.81 mg. So I skipped to say that FG is mg. Remember that this is always true. Minus this one, so I'm going to set equal to 0. Or in other words, FA will be this plus this minus that. So let me solve for, well, let's write this out and then I'll solve for FA. So 35 times 9.81, 58 times 9.81. Okay. 2962 minus FA minus 343.35 newtons minus 568.98 newtons, like that, equals 0. Okay, so if I'm going to solve for FA, if I add this over, basically, that's the easiest way. Then I have FA. So if I add that over, these all stay the same, equals the 2962.2 newtons minus 343.35 newtons minus 586.98, sorry, 8 newtons in the way. Okay, well, you get it. So FA 2962.2 minus 343.35 minus 586.98. Perfect. We get this is 2031.87 newtons, like that. So these both increase from the previous problem. If we took a look, these were roughly 2,000 and 1,700, and then if you look at this one, you can see that they got bigger because there's more mass to consider and more torques involved. So that was the main point of that, is those forces change values, as you might imagine. So it was similar, we just had to add an extra term. Okay, I think I have enough time to do the next one. Another equilibrium problem. So now I'm going to solve this problem, which uses torques. So this is a static equilibrium problem. So the question is essentially, let's see, get my marker going, there we go. So we have this traffic pole as seen right here. We know the length of this pole, like this right here, and we know that this is 7.5 meters, like that. We know the mass of the pole. We know the mass of the traffic light. The question is, what is the tension here? And then what is the wall forces? So the wall is going to exert a force in the y and in the x. So what are these components and what is this tension right here? So first let's put all the forces that are acting on the pole right here. So we have this one right here. You can see we have another force right here. And then the pole itself has its own weight. This is weight traffic, like that. So we have 1, 2, 3, 4 forces acting on the pole. Now if I were to look at the sum of the forces in the x and the y, we would have 1, 2, 3 unknowns. So this is very difficult, which is why I'm going to actually choose A as my pivot, and then start off by solving it as a torque problem to eliminate this first, and then we'll use the information about our tension to solve the rest of this problem. So I hope you notice the red flag, and notice that all of these do not make nice right angles, right? You can see that this is not a right angle, this is not a right angle, this is not a right angle. It makes this really difficult to solve. So a trick you can do is you can actually move the forces so that they are actually in line with your system. So what do I mean by that? So I'm going to move this. So instead of right here, I'm going to put it over here. And then if you notice, the force is now perpendicular. If I put T, I'll put it in green, the moved force from the pivot. So if I put this here, and then use this distance, which we happen to have, you can see now the tension is at a right angle to here. So this is a technique you can use. This gives us the ability to solve this. So I could do the same thing with these, is I can move this force down this imaginary horizontal line. So if I move this down to here, I can use this distance, I'll call it R1 for labeling purposes, and now these are perpendicular, and then if I move this down to here, R2, these are perpendicular. So that's how I could solve this problem when I have, something like this. This is not a standard problem because these are not at right angles. So you could use sine, but the beauty of this is it also makes these completely in one direction. Notice that these are completely y and these are completely horizontal, which makes things a little easier to solve. So with that said, I'm actually going to solve this as a torque problem using the green, okay? Now we can actually move these forces down because of our rules about vectors, which means we can move any force vector anywhere in the screen as long as we keep the direction and the magnitude the same. So notice that these are the same direction and the magnitude, we're not changing these numbers. Okay, so let's start off by analyzing our torques. So this one will make this boom, or pole, if you will, go counterclockwise, right? We're going backwards, so this is counterclockwise, so this will be a positive number. This is going to go, looks like clockwise, so this will be negative, and this will be clockwise, so this will be negative. So look, by putting the pivot here, we don't even have to worry about this, which is really nice. So clockwise minus counter equals 0 because it's in equilibrium. Counterclockwise torque. Okay, so that's going to be our tension. Now the distance from here to here they gave to us is 3.8 meters, which is really nice. So remember, tau is force times distance, and as long as these are perpendicular, we don't have to use the sign. Great, and that's our variable that we're looking for, is tension. Now let's look for these. So notice I don't have this distance right here, but I could figure it out. If you notice, this angle here is the same as this angle here due to alternate interior angles. And I do know this distance from here to here. This is half of the rod. So actually what I could do is find R1, and I'll do this as a note. R1 is going to be a cosine because we have the hypotenuse, and this is adjacent to R. So R1, I can write it as actually, let me do it like this. So cosine of 37 degrees is going to be equal to adjacent, which is our R1, over hypotenuse. So R1 will be 3.75 cosine 37, like that. So I'll do that. This says 2.99, so I'm going to go ahead and just go with 3 right here. So this would be mg, which is the mass, in this case, of the pole. So this is going to be 12 kilograms. So this is the force times the radius, like that. And with the same logic for this one, R2, we know the length of this, which is a 7.5, this, so R2 is going to be 7.5 meters times cosine 37 degrees. So I will do that. This one gives us 5.98. I'm going to go ahead and just go with 6. So the mass of the traffic light times g will give it the weight times 6 meters. This is all going to equal to 0, like that. So why don't I go ahead and solve this. And I'm running out of time, but I get t times 3.8 meters minus, so I did these two, is 9, so did that number, actually the video is going to stop I'll do this in the next part.